everyone, welcome back. Now we're moving on to talking about gases and specifically the ideal gas law. And this ideal gas law is exactly what it sounds like. It's a law dictating the behavior of a gas that is experiencing ideal conditions. Ideal conditions meaning that the gas, because since molecules attract each other, sometimes gases don't move in an ideal way. But ideally, there's no intermolecular forces happening, so we neglect the interactions between molecules of gas. So they're just bouncing around, and we're assuming they don't touch on each other when they bounce. So really, this law is not really applicable to real life, but it makes for a pretty close estimate. And in general chemistry, this is all we have to talk about, really. So in this case, we have pressure times volume equals number of moles times the gas constant times temperature. And the best way to learn how to use this law is to just practice with some problems. And so let's try our first example. So it says a sample of CO2 occupies 0.3 liters. So given is volume, V is equal to 0.3 liters at temperature degrees Celsius, 10 degrees Celsius. So we have 10 degrees C. And our pressure is 750 torr. What volume will the gas have at 30 degrees Celsius and 750 torr? So now we want to know what V is if T is equal to 30 and P is equal to 750 torr again. And that would be part A. So now we're talking about the same sample and the same amount of sample. So the number of moles in these guys would be the same. And since we're comparing, we can say, okay, so let's say that this is in our given, it's V1, T1, P1, and we're looking for V2, T2, P2. So the best way to do this is compare using the ideal gas law. And in doing this, we'll find a derivation of the ideal gas law that once you see it once, you could just skip this part. And so we can divide it by the total ideal gas law of the second portion, which is P2 V2 equals N2. R is a constant throughout T2. So now we know from what we're given in our goal, our P1 and our P2 is the same, right? So P1 divided by P2, 750 divided by 750, these guys are equal to 1. And it's the same identity and same number of moles. So these guys also equal 1. And the gas constant, it's a constant, so it'll be the same. So this is equal to 1. So what we're left with is called Charles's law. And it's V1 over V2 equals T1 over T2. And what we're looking for is V2. So we can go ahead and isolate V2. So we multiply V2 to both sides, and then we divide over T1 and multiply T2. So doing that quickly, we end up with V2 is equal to V1 times T2 divided by T1. And now we can just plug in. So V2 equals V1 times T2 divided by T1. And plugging what we decided was our 1s and our 2s before, it's going to be 3 liters. And now the trick is, whenever we're using ideal gas law, this R is always given in units Kelvin. So even though we're not even using the R, whenever we talk about gases, we want our temperature to be in Kelvin. So let's change that out really quick. So we know that T1 is equal to 30 degrees Celsius. And to change from Celsius to Kelvin, we just add 273 Kelvin. And that gives us 303 Kelvin. And then we know, oh, sorry, that was T2. And T1 was 10 degrees Celsius, meaning that it's 283 Kelvin. So now we plug in our T2, which is 303 K, and 283 K. And now we have Kelvin on the top and the bottom of our fraction, so they cancel. And we end up with times 3.21 liters as our answer. So expanded a little bit, or it expanded quite a bit in those 20-degree difference. Oh no, it didn't. I put 3 but not 0.3. So actually we just move the decimal place over. So it's 0.321 instead of that. That's why it's always important to look back and make sure your answer makes sense. So in 20 degrees difference, we expanded by 0.021 liters. And that would be our answer. Now you can try the second part on your own.